here we go. Oh. Okay, so guys, this is what we are up to today. We are going to draw what are called Lewis dot molecular structures. Now guys, if you think about the way this class rolls, you learn something new, you do some homework, you come back the next day, we learn something else new, you do some homework. Eventually, when you've learned enough new things, we do a lab. After we've done that a couple times, you take a test, right? That's sort of the way this thing goes. Well, guys, this ain't gonna go that way. And here's why. It is really, really, really important. Guys, there is not one topic this year that we have spent more than one day on. This we're going to. So when I see you on Tuesday, you're going to walk in here, we're going to grade the homework, and I'm just going to hand you another homework assignment, which is exactly like the homework assignment you just graded, to give you even more practice with these. Guys, I'm sending to you the message that these are critical. So what you're going to find out as you start doing your homework today, and you're going to have about half an hour to work on your homework, is these start kind of gentle. They're pretty straightforward. I did that on purpose to help you get rolling. Then guys, quickly they become more difficult, and then the ones that you're going to see on Tuesday can at times be sort of nasty. But guys, it's important that you learn how to do these. So Lewis dot molecular structures. So you ready? Let's talk about what they are. When you think about Lewis dot structures, what comes to mind? The last test, right? The very last part of the last test was drawing Lewis dot structures. So guys, let's remind ourselves, what do the Lewis dots represent? Valence electrons. How many dots do all these have? 1 and 2 and 2 and 3 and 4 and 5 and 6 and 7 and 8, right? And what do you remember about the first two dots? They're paired up because where are they? Oh guys, come on, seriously. S sublevel, right? And then what about the next three dots? Why are they unpaired? Because they're in the P and they spread out, and then 6, 7, and 8 pair. Is it all, yeah, you're quiet, but you remember, right? Okay. So guys, here's what we're going to do. We are going to draw Lewis dot structures again, but instead of doing those for atoms, we are going to do those for molecules. Now let's see if you figured this out. Guys, what kind of bonds exist in molecules? Covalent, ionic, or metallic? Covalent bonds. And what atom pairing leads to covalent bonding? Non-metal. Guys, okay, now I'm really concerned. I understand that we started the day distracted, and I have to attribute that to the fact that you're at least as excited as me to be gone for Thanksgiving. But now I'm concerned that you guys are maybe just recording homework scores and not actually learning anything. So maybe we should slow down. So guys, molecules, are you comfortable with the idea that those are covalently bonded substances? What happens when something bonds covalently? Stealing? Not stealing, sharing. And what atoms are able to share with each other? Small, strong atoms, which are the non-metal. Are you really okay? And it's just kind of a weird start to the day. Okay. So guys, with that said then, this is what you're going to be doing today. So here's the way this is going to go. We are going to tie this back to what you learned last time. Then, moving forward, we're going to review valence electrons to make sure you're clear. Then, guys, I'm just going to give you the steps for writing these. It's frankly tricks that I learned in college that make these a lot easier. And then, guys, we're going to do 4 of these together, and then you're going to have a chance to work on them on your own. So, guys, before we get started, I should have mentioned this. You need a pencil. Don't do this in pen. If you want to take your notes in pen, that's fine. But when you start drawing these Lewis dot structures, you've got to have a pencil. So if you don't yet, when we start doing these, I can share one with you. But here we go. So guys, getting started, tying this back to what we already did. So it sounds like some of you need this review. Don't try to write this down though, because you won't have time. So, guys, this is where we ended the day last time, right? And we said ionic bonding leads to what kind of compounds? that leads to salts. So the nonmetal loses or picks up the electron from the metal, that forms ions, that forms salts. And then guys, we wrapped up the day talking about metallic bonding. We've got these atoms that are weak and they all dump their electrons into the free space. That leads to this concept of the sea of electrons, and that was metallic bonding. Then guys, in the middle of that, we talked about covalent bonding, which is sharing bonding that leads to molecules. Well guys, the deal is this. We are now done with ionic and metallic bonding. We are not going to talk about those anymore for the rest of the year. So everything else that we are going to talk about is covalent bonding, which leads to molecules. And today we're going to learn to draw what are called Lewis dot molecular structures. So you guys connecting the dots? You're okay? All right. So guys, with that as a background then, let's talk about the things that you need to remember about Lewis dots. So guys, don't write these down, but let's make sure you can answer these questions. So guys, when we talk about Lewis dot structures, what do the dots represent in these structures? The valence electrons, right? And which ones are the valence electrons? The ones on the outside, right? And they are the S's and the P's. Now, how many of them can there be? 8, right? And of these 8 electrons, we already said, which sublevels are they in? S and P. Now, how many of them are in the S and how many of them are in the P? 2 in the S, 6 in the P, right? So, with the 2 in the S and the 6 in the P, how many sublevels are in the S? Remember? Or how many, it's not sublevels, orbitals. How many orbitals are in the S? 1. It's a sphere. And how many orbitals are in the P? 3 in their dumbbells. Is that all good for you? Because it's important you remember this. Okay. So guys, with all of that said, this is where you need to start taking notes. So all of this is going to be the framework on which we're going to build these Lewis dot molecular structures. To do this though, you need to understand something called the octet rule. And you want to scratch this down. But most of you could figure this out without me really saying it. Because guys, what does the prefix oct mean? It means 8, right? So what about 8? Well, guys, there is a rule in the chemical world that says something about 8. Why 8? Because that's how many valence electrons there can be. And it says this: when atoms bond together, they are most stable when they have a complete shell of 8 valence electrons. So why do atoms bond at all? Because they're trying to become more stable. And how do they become more stable? They become more stable by getting 8 valence electrons. This is something you need to know, yeah. Because you don't need to know that, well, you already know the answers to these questions. But if that idea of the octet rule seems a little vague to you, you may want to scratch it down. It's certainly something that I could ask you to talk about and explain. So the octet rule again, guys, says these things want to have 8 valence electrons. So how do they get 8 valence electrons? By bonding, unless you're a noble gas, and then you've already got 8. You okay? Can I go on? Okay. So guys, now making the connection. In order to draw Lewis dot molecular structures, we need to start by reminding ourselves how to do Lewis dot atomic structures. So guys, do this in your notes. It'll take you about 2 minutes. If you feel like you really know how to do these anyway, because you're going to learn some things along the way. Guys, draw the Lewis dot structures, just like you did on the last test. Draw the Lewis dot structures for these 5 atoms. You're going to find out that I did them in this order for a very specific reason, but draw the Lewis dot structures for these 5 atoms. And then we'll talk about them. Oops. This is what you did on the last test, yep. Yep. was I right about why you guys are so distracted? Is it a Thanksgiving thing? Or is it something else? You're not going to tell me. You guys all done? You're good? Okay. So guys, you're about to learn something. You ready? So take a look at where hydrogen is. It's over here, right? So how many dots does it have? One. But now guys, check this out. This is old school. You know how to do this. But now what you need to understand is that these Lewis dot structures are about to become puzzle pieces that we're going to put together to form molecules. So you see this one electron, and you see this spot right here where there is not a paired electron. Guys, that is what we call a bonding site. You don't need to draw the box unless it helps you focus your attention. But guys, that is a bonding site. It is a place where hydrogen can form a bond. Now, notice this. Hydrogen only has one bonding site. It doesn't have 7. Guys, these empty spaces over here are not bonding sites. So bonding sites are places where there is one, but not a second electron. So carrying that concept through, nitrogen has got 1, 2, 3, 4, 5 electrons. Y'all okay with this? So if you understand that this is the Lewis dot structure for nitrogen, how many bonding sites does it have? Do you see them? There's 1, there's 2, there's 3. 3 bonding sites. And guys, this is not something that you're actually going to be drawing in. I'm just putting the boxes there to draw your attention. Yeah. Exactly. And so think about what this really means though, Tyson, because this is a p sublevel, right? So you've got a p orbital with an electron in one lobe, but not in the other lobe. And that's what allows it to bond, are these half-filled orbitals. Is that okay? So, but what Tyson said is right. It's one, but not the other. So guys, oxygen with 6 valence electrons looks like this. How many bonding sites does it have? 2. And then chlorine with 7 valence electrons, just like all the halogens, 7 valence electrons. How many bonding sites does it have? 1. So guys, why did I put them in this order? Well, I wanted you to see that hydrogen only has 1 bonding site, and then we went 3 and 2 and 1 bonding sites. Now we got to talk about carbon. Guys, how many dots does carbon have? 2. 4, 2, 4, 4. So, guys, but what I'm thinking is, what do you know about the first 2 dots? They're together because they're in the S, and then 3 and 4 are unpaired, and it looks like this, right? So these are the 2 electrons in the S, and then these are 2 electrons in the P. So, given this picture, how many bonding sites does carbon have? 2. Guys, it turns out this is not correct. Now, we're going to talk about what carbon actually does. We're not going to explain it. If you want the explanation, come back for AP next year, although that's not enough motivation to spend the entire year in AP. But we do talk about this in AP. But the bottom line is this. Guys, when we draw these Lewis dot structures, we are going to, and you want this in your notes, we are going to spread out the electrons as much as we possibly can. So we are no longer going to put the S electrons together. We are going to spread them out as much as we can, and when we do, carbon now looks like this. Now guys, when we do that, how many bonding sites does carbon now have? 4. And that is actually what carbon does. That is also why we are carbon-based life. You guys understand that, right? Every living thing on this planet is based in carbon. Now guys, why would carbon be the logical choice if you're going to try to make things that are alive out of any element? It's the maximum number of bonds. And guys, if life is complicated, and it is, the thing that you would want to use as the foundation for your complicated molecules would be the thing that has the most bonding sites. So guys, either evolution took the most logical course or God is smart. And however you sort that out is fine. But in either case, carbon is the obvious choice to base life in because it has the maximum number of bonding sites, which is 4. You get the idea? Okay, so now what you need to do is this. Go back to hydrogen, nitrogen, oxygen, and chlorine, and obeying this rule that says we're going to spread out the electrons as much as we can, go back and redraw hydrogen, nitrogen, oxygen, and chlorine. You done? It doesn't change anything. Guys, you can't spread out one electron. You can move it around, but that doesn't spread it out. Now, what about this? What if we wanted to spread out this pair of electrons in nitrogen? Well, it's got to go somewhere, so it's got to create a pair. If you've got 4 places and 5 electrons, something has got to pair up. Now, what if we try to spread out these 2 pairs? Again, they've got to go somewhere, and you still end up with 2 pairs. What if we try to spread out these 3 pairs? Same thing. Eventually, you're going to end up with 3 pairs. So guys, the bottom line is this is the only one that it changes anything for because carbon and its group mates are the only ones that have an empty p that you can spread the s electron into. You get the idea? So it only changes the carbon group elements. You good? Okay, so guys, with that said then, here we go. We are now going to start pulling all these ideas together and drawing what are called Lewis dot molecular structures. So guys, do this with me. Let's show you an example. So here's oxygen. Make it about 1 inch tall, move it down a couple lines, and put it right in the middle of your paper. So guys, oxygen looks like this. We've already talked about the idea that it's got 2 bonding sites. So let's start forming some bonds. And guys, don't write this down until the animations are done. But you can see that oxygen's got a bonding site right there. Well, now let's bring in a hydrogen atom. Don't write it down yet. So now we've got a hydrogen atom, and it also has 1 bonding site. So when these atoms approach each other, they lock together, bonding site to bonding site, and we end up forming that sharing covalent bond that bonds the hydrogen to the oxygen. Now, guys, we're not done yet, right? Because we've got another bonding site right here, and if we bring in another hydrogen, now we have locked their bonding sites together, and we end up with this, which is a water molecule. So go ahead and draw it. So that's what you're going to be doing for the next 2 class periods, is locking these Lewis dot structures together to form molecules. But guys, here's the trick. Watch really close because this is subtle. This is not the way we're going to draw these, but let's talk. What does this pair of electrons right here represent? A bond. What kind of bond? A covalent bond. But we are not going to draw these covalent bonds like this. We are going to replace these pairs of electrons with lines, and you want to put that in your notes. So guys, the line, but I wouldn't erase the dots, because guys, the lines represent 2 electrons being shared. So with that said, you now need to understand that we've given names to these pairs of electrons. Guys, these electrons are not involved in bonding, and these electrons are involved in bonding. So the ones that are involved in bonding, we call bonding pairs or shared pairs of electrons. And then the electrons that are not involved in bonding are called non-bonding pairs or lone pairs of electrons. And guys, we are going to use the term shared pair and lone pair, but lone means non-bonding and shared means bonding pairs of electrons. Okay, so here's the scoop, guys. There are a lot of chemistry teachers, both in high school and college right now, that would just say, let's start drawing Lewis dot structures, and you draw the Lewis dot structures of the atoms, and then you figure out how to put them together as molecules. Guys, I would argue that that's not the best way to teach this. See, I could have you do that. I could have you draw oxygen with 6 dots. I could have you draw hydrogen with 1 dot, then move the hydrogen into the oxygen. But guys, eventually that just becomes unnecessary. So, and you don't need to write this down, but it turns out, guys, that in order to draw these molecules, it isn't actually necessary to draw the Lewis dot structures of the atoms first. You can actually draw the molecules without doing the atoms first, but what you need to know are a couple of shortcuts. So what I'm going to do on the next slide is I'm going to give you all the shortcuts, and I'm just going to have you write them down. Not going to try to explain them, just write them down, and then we'll do 4 examples, and we'll start to apply these shortcuts, and it'll make sense. So guys, these are the shortcuts and the hints and the steps that make these easier. So we're going to call them steps. So step number 1 is this. When you are drawing these Lewis dot structures, molecular structures, what you're going to do is you're just going to get all the atoms on the paper and you are going to single bond them together. Guys, this is, when you start doing this, this is where you're going to want to start writing in pencil. You can do this in pen if you want. But when you start applying these steps, do these in pencil because they involve a lot of erasing. All right, so you get them all on the paper and you single bond them together. Now guys, when you do that, one of the things that you need to be thinking about is make them symmetrical. You may just want to write down the word symmetrical. As a matter of fact, why don't I just write down the word symmetrical? And we'll even capitalize the S. So guys, when you do this, you want to do these symmetrically. Now guys, what does it mean to be symmetrical? Same on both sides. So guys, if you've got something that's symmetrical, it's the same on both sides. So for example, if you're doing a nitrogen dioxide molecule, you've got a couple choices. You could go oxygen, nitrogen, oxygen, or you could go oxygen, oxygen, nitrogen. Which one of those, the top or the bottom one, is more symmetrical? The top one. And that's what you're going to do. You are going to write these so that they are symmetrical. So that's what that is telling you. Now guys, the next thing you need to think about, and this will become important when you get into the homework in like numbers 6 and 7 and 8. They get a little crazy. Guys, many times you're not going to know exactly what order to put these, even as you're trying to make them symmetrical. So the bottom line is this, and you'll get better at doing this as you practice. Many times the bonding order for these molecules is given in the formula. And when you get into these in homework, you'll understand better what that means. Then guys, another helpful hint is this. Many times when you're drawing these structures, carbon will be in the middle. Almost always. And guys, you already understand this. Why would carbon be in the middle? Maximum bonding sites. That's why we are carbon-based life. Now guys, in addition to the idea that carbon is always in the middle, there are some atoms that are never in the middle. And those include hydrogen and the halogens. And if you don't remember where the halogens are, you may want to look at your periodic table and remind yourself. Guys, halogens and the hydrogen and the halogens will never be in the middle. So let's talk about why not. Okay, baby, my board has been a mess. You gonna let me draw? Here we go. Okay, so hydrogen, and let's pick chlorine as our sample halogen. So guys, talk to me. Why will hydrogen and any of the halogens, chlorine was the example I chose, why won't those be in the middle of a molecule? They only have one bonding site. They can't be in the middle. So guys, think about it this way. If I had you all stand up and said, all right guys, we're all going to hold hands and make a human chain. If there was somebody in this class that was an amputee and they were missing an arm, where would they have to be in the chain? On the ends. Because if we tried to stick them in the middle, they could reach this way, but they couldn't reach that way, and they can't be in the middle, right? Well, guys, you can think of hydrogen and the halogens like an amputee. They only have one arm, if you will, one bonding site to reach out and bond, and as a result, they can't be in the middle. The analogy is pretty good. Okay, so the last one then, oh, really? Oh, man. This is ridiculous. Okay, then the last one of these guys that you need to keep track of is, well, not the last one. The next step is once you've gone through all of that process, then the next thing that you're going to do is you're going to count up all the valence electrons for each of these atoms. And when you do that, notice that I just mentioned there with the dash, keep an eye out for ions, and I'll explain what that means in a minute. Some of you are going, wait a minute, I thought we were talking about molecules and those don't contain ions. And you're right. I'll show you what I mean in a second. So then guys, once you're done with step 2, then step 3 is to spread out all the unused electrons as much as you possibly can around the molecule, spreading them out evenly. And guys, when you go through this spreading out process, and I'll show you why in a minute, but when you go through this spreading out process, you always want to fill the hydrogens or the halogens completely first. And then guys, finally, and this is the last of your notes, and then we're going to look at examples. Step number 4 is check for and fill octets by creating multiple bonds. Yeah? Uh-huh. Only affects the carbon? Yes. I see what you're saying. Oh, so going back a little bit in time. And the answer is because boron as well. So boron's a metalloid, right? It doesn't form covalent bonds. It is so weak that it actually forms ionic bonds in salts. So you're right that if boron and even like beryllium, right? If it were strong enough to form a covalent bond, we would spread them out, but we don't think about that relative to things like aluminum and beryllium and boron because they don't covalently bond because they're so weak. So guys, this is it. These are the steps that we are going to use in order to figure out the structures of these molecules. We're going to do 4 examples. We'll step through this and help you understand the pattern to doing these. And then guys, you're going to have 15 of these to play with in homework today. You'll end up with about half an hour to work on these in homework. And you'll get good at these. Well, you'll get better at these. And then on Tuesday, we'll really fine-tune things. And then after Thanksgiving break, we'll move on and start looking at what these look like 3-dimensionally. So, you guys all caught up with me? You're good? Okay, so we're going to do 4. We're going to start with some easy ones. They're going to get progressively more difficult. But guys, ask questions, follow along. Here we go. So this is the way we're going to do this. The first molecule that we are going to look at is what is called nitrogen trichloride. And you'll notice that off on the right-hand side, so what you want to do is off to the left, write down NCl3 in your notes as examples. And then off to the right, we are going to identify the number of shared and lone pairs around the central atom. So how do we approach these? Well, guys, what's the first thing we need to do? Step 1, get everything on the paper and single bond it together. Guys, please do not write this down. So we've got NCl3. What's wrong with what I just did? There's all sorts of stuff wrong. What's wrong with it? First of all, it's not symmetrical. What else is wrong with it? They're not all connected to the nitrogen, but maybe they won't be. What else is wrong with it? Look at step 1, guys. What are your rules under step 1? What can never be in the middle? The halogens. Guys, chlorine cannot form 3 bonds. It's only got 1 bonding site. That's what that means. Chlorine is the one-handed man that can't reach out in more than one direction. So this is wrong because it's not symmetrical and because the halogens can't be in the middle. So how do we get around both of those constraints? We go like this. And chlorine, man, my board is struggling. You're just going to have to bear with me, guys. I need a new board. And now we've got nitrogen in the middle. We've got the 3 chlorines. The chlorines aren't in the middle. Everything's on the paper, single bonded together. And we're now done with step number 1. You okay? Okay, now step number 2. It says count up the valence electrons that you've got. And guys, here's how you're going to do this. Go over to the abbreviation of the element and ask yourself, how many valence electrons does nitrogen have? 1, 2, 3, 4, 5, right? So you'll just go up here and nitrogen has got 5 valence electrons. Now, how many valence electrons does chlorine and all of the halogens have? 7. But how many chlorines are there? There are 3. 3 times 7 is 21. And you add those together and we have 26 valence electrons to muck around with. Now, how many, and this is step 3, how many are already used in our molecule? Well, guys, what do each one of these lines represent? 2 electrons. So we've got 2, 4, 6. So we have already used 6, and that leaves us 20. Now we're really ready for step 3. We are going to get all 20 unused electrons on the paper. Now guys, what does the little subpoint underneath step 3 say? Where do we have to put the electrons first? On the halogens. So we will not start with nitrogen, we will start with the halogens. So we're going to go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So there are 18 electrons around our halogens. How many do we have left? 2. And we will just put those 2 right here. There we go. So now we have all 20 electrons on the board. So now step 4, we need to check for the octet rule. That's the 8 rule. So all of the atoms on the board want to have 8 electrons. Guys, please don't do what I'm about to do. But mentally, here's what you're going to do. I'm glad you think that's funny, because frankly, this is really getting frustrating. We're going to have a bake sale and we're going to buy me a new board. Okay, so here we go. And then we're going to go here if this stupid thing will let me. And guys, mentally envision this picture. How many electrons are around that chlorine atom? 2, 4, 6, and what does that represent? 2, so that's 8. So this chlorine has got 8 electrons. It's happy. So now guys, what about this chlorine? Does that chlorine have 8 electrons around it? It sure does. Now what about this chlorine? Does that guy have 8 electrons around it? Sure does. Now watch this. What about the nitrogen? Well guys, that nitrogen also has 8 electrons around it. 2, 4, 6, 8. That's the magic of covalent bonding, is these electrons count for the 8 in both atoms. So guys, all of these atoms have 8 valence electrons around them, which means that they are all happy. And this then, and I'm just going to put that back in red, this then is what NCl3 looks like, or the model kit, it actually looks like this. You've got the nitrogen in the middle, you've got the 3 chlorines around it, and this is what NCl3 looks like. You get the idea? Okay, so now we need to identify shared and lone pairs. And guys, we are only going to do this for the central atom. So how many shared pairs of electrons are on that nitrogen? 1, 2, 3. So there are 3 shared pairs of electrons. How many lone pairs of electrons? Just 1. So that would be 3 shared and 1 lone pair. And guys, notice we only do that for the central atom. You guys good? Questions? You sure? All right. Let's try another one. And now we're going to try this, C2H4. And guys, again, these are going to get progressively more complicated. So guys, looking at rule number 1, or step number 1, it says get them on the paper. Guys, which of those hints under question or step number 1, which of those hints applies to this molecule? Hydrogen's never in the middle. Any of the others? Carbon's always in the middle. And do it symmetrically. Guys, watch this. C and C and H and H and H and H. Yeah? Why no? It's not symmetrical. So guys, you need to be keeping those rules in mind. So how can we do this in such a way that it is, in fact, symmetrical? And guys, the answer is this. Now understand that you could have just as easily done this. You can take one of these and you can put it up here if you want. Up, down, left, and right does not matter. You can do that however you want. You'll find out later that three-dimensionally they're quite different. But guys, the bottom line is you're going to go like this, and then you're going to put a hydrogen on both of those. That is now as symmetrical as you can make it. Okay, so what do we do next? Count all the electrons. How many valence electrons does carbon have? Not 6, it's 4. 6 electrons, but only 4 are valence. But 4 times 2 is 8. Now, how many valence electrons does hydrogen have? 1, but there are 4 of them, so this is 4, and that then gives us 12. Now, how many are already on the board? Well, we've got 2, 4, 6, 8, 10. So 10 are already on the board, so that only leaves us 2. Now we've got to put these 2 electrons on the board. Can we put them on the hydrogens? We can't. Guys, hydrogen only has an S sublevel. Hydrogen does not have a P sublevel, so there's nowhere to put electrons. So as soon as hydrogen forms one bond, it's done. So now, where do we put the electrons? And guys, here's the thing that's cool about the way I'm teaching you to do these. It doesn't matter where you put them. You could put both electrons there, and that's fine. You could also do this. You could put both electrons here, and that's just fine. You could also put 1 electron in each, and that is also just fine. It doesn't matter where you put them. You just got to get them on the paper. Sydney, are you okay? All right, but no, I heard you going. I didn't know if you guys were talking. Are you okay though, Tice? Are you okay now, though? Do you see? Guys, and are we okay with where the 8 and the 4 came from? Does anyone want to talk about it? Okay, so now, guys, we've got the 2 electrons on the paper, so now we need to check the octet rule. Lauren, can I help? Are you sure? I'm not being weird. I really want to help, because if you have questions, it's not just you. So, are you okay? Okay, so guys, now watch. It's now time to check the octet rule. You don't need to draw these circles, and I won't draw them again after this example, but let's just take a look. Does hydrogen have a full octet? No, but it doesn't. Once hydrogen forms one bond, it's happy. So hydrogen is the only element that violates the octet rule. Now guys, what about this? Is that carbon all full up with 8? Yeah, it's happy, right? It's got its 8 electrons. Now guys, what about this carbon? Is this carbon all full up with 8? No, it's only got 6. So what are we going to do? How can we give this carbon 2 more electrons to give it 8? Well, we can't just draw in 2 electrons because we only get 12, and that would be 14. So we can't just magically make electrons appear. So how do we give that carbon 2 more electrons? And guys, the answer is this. Watch. What we're going to do is we are going to take these electrons off of that other carbon atom, and we are going to move them into the middle. Now, this carbon has got 8, and this carbon has got 8, and we just formed the C2H4 molecule that actually has a double bond between the carbons, giving both of those carbon atoms 8 valence electrons. Did you see it? You okay with it? Okay, now let's do shared and lone pairs. So guys, this gets a little funny. Just hear me out. When we do shared and lone pairs, we only do it for one atom. And that's the atom that's in the middle. So guys, which one of these carbon atoms is in the middle? Either one. It doesn't matter which one you choose because they're the same. So say that we choose this carbon atom. How many shared pairs are on that carbon atom? 1, 2, 3, 4. So there's 4 shared pairs. How many lone pairs on that carbon atom? None. There are no unbonded pairs of electrons. Now guys, what if we'd done this? What if we had chosen, what if we'd chosen the other carbon atom? How many shared pairs on that? 4. 1, 2, 3, 4. How many unshared pairs? Lone pairs? None. So it doesn't matter which one you choose, they're the same. You guys good? Questions? No? All right. Let's do 2 more and we're done. So guys, the next one that we're going to do is NO3 minus 1. This is what they call nitrate. It's actually a compound that they add to meat. Like if you go to Costco and buy meat, you'll notice, guys, that the meat always looks all red and healthy and perfect. Because the only reason it looks red is because they put nitrate on it, and the nitrate keeps it from browning. And sometimes you look like underneath the meat's all brown. It's not unhealthy, it's just not that red color because they didn't get nitrate on the bottom as well. Anyway, so nitrate, we're going to draw its structure. So which one's going to be in the middle, do you suppose, in order to make this symmetrical? The nitrogen or the oxygen? The nitrogen. So we're going to go nitrogen and oxygen and oxygen and oxygen. And again, up, down, left, and right doesn't matter. Just get it on the paper, single bonded together. Now, guys, we've got to count electrons. Are y'all okay with nitrogen having 5? How many valence electrons does oxygen have? 6. But how many of them are there? 3. That would be a total of 18. And now, guys, this is what it means to watch out for ions. What does it mean that this molecule has a -1 charge? It got an extra electron. So we get a bonus electron to play around with. So that gives us a total of 24 electrons. Now, how many are already on the paper? 2, 4, 6. So that gives us a remainder of 18 electrons. So where are we going to put them? Well, let's just get started. So let's go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So guys, we've got 12 on the paper. That means we've got 6 left. What are we going to do with them? Well, we could do 6 and 0, and that would be fine. We could do 2 and 4, and that would also be fine. It doesn't matter what you do with them. This is always going to work out. So what do you want to do? 2 and 4 or 0 and 6? 0 and 6. All right. 1, 2, 3, 4, 5, 6. Okay, so now guys, I'm not going to draw circles. Let's do this mentally. Does this oxygen have its 8 electrons? 2, 4, 6, 8. What about this one? 2, 4, 6, 8. What about this one? 2, 4, 6, 8. What about the nitrogen? It does not. It's only got 6. So how can we give nitrogen 2 more electrons? Create a double bond. So where do we do that? It doesn't matter. We could take electrons off of here, or off of here, or off of here. It just doesn't matter. So let's do the one on the left, just because it's closest. And we'll take 2 electrons off of here, and we will move them into the middle, and that then makes NO3. And guys, it looks like this. This is what a nitrate molecule looks like. You've got the double bond to one of the oxygens. Again, you'll be playing with these model kits right after Thanksgiving. But guys, this is what this looks like. Now there's 2 other, well, let's do shared and lone pairs. So central atom, how many shared pairs? 4. How many lone pairs? None. Now guys, the last thing that you need to know is this. When you draw the Lewis dot structure for ions, you've got to put them in brackets and add the charge. So that's what the Lewis dot structure would look like. Are you guys doing okay with shared and lone pairs? Is that okay? Please ask questions if it's not. Okay guys, one more and we're done. Carbon monoxide, the silent killer. When our furnaces don't run right, they dump a bunch of carbon monoxide into our homes. It's tasteless, odorless, colorless. You don't even know it's there. It actually binds up with your blood and keeps it from carrying oxygen, disabling the hemoglobin in your blood, and you die in your sleep and you don't even know it. It's crazy stuff. But what does it look like as a molecule? Well, guys, let's get it on paper. So we're going to go carbon and oxygen. So there's our beginnings of the molecule. Now we need to count electrons. Carbon has got 4, oxygen has got 6. That gives us a total of 10. There's 2 on the board, and that gives us 8. Now guys, you just got to trust me on this. You can't do this wrong. You could go 4 here and 4 here. You could go 6 there and 2 there. You could go 6 here and 2 there. It doesn't matter. You can't screw this up. So let's just go 4 and 4, just because I suspect that's what you would do because it looks symmetrical. So now we've got all the electrons on the board. Now, we've got to check octets. Is this carbon happy? It's only got 6. Is the oxygen happy? It's only got 6. So let's start to take care of that. So we're going to come along, we're going to take off 2 of these electrons and move them into the middle. Now guys, how many electrons are on this carbon? 6. How many are on the oxygen? 8. So the oxygen is now happy, but the carbon is not. So now we've got to give some electrons back to the carbon from the oxygen. So we'll take 2 off of the oxygen, move them in the middle, and now everybody has 8, and that would be the carbon monoxide molecule that actually looks like this, and it's got a triple bond between the carbon and the oxygen. So now, guys, let's do shared and lone pairs. Which one of these atoms is the central atom? It doesn't matter, because regardless of the one you choose, there's 3 shared pairs and 1 lone pair on either one of the atoms. It doesn't matter which one you pick. You guys good? Okay. So guys, what we're going to do today is we are going to work on that homework assignment that I gave you. I'd encourage you to work in groups. Do this on another sheet of paper. You're going to need a lot of space. If you have questions, let me know. Again, on Tuesday, we're going to grade this, and we're going to do another set of these. The answers are on the wall. They're also posted on our website, so feel free to grab your smartphones and look them up.